ratio test. Okay, so when we use the ratio test, we're just saying un plus 1 over un. That means wherever there's n, we're going to say wherever there's n plus 1, and we're going to divide it by the original series. Okay, so if our r, which is the limit we're going to compute, is greater than 1, that means the series diverges, and if it is less than 1, that means the series converges. Okay, so let's say we have encountered a situation where we have 1 plus 1 over n to the power n. This is equal to e, which is the exponential. Okay, you can just try, you can say 1 plus 1 over 100 to the power 100. You see you're going to get a number that is equal to e, which is 2.7. Okay, you can try another number. Okay, so what we're going to do here is that we're going to say limit as n approaches infinite of un plus 1 over un. So this is equal to, I'm going to say n plus 1 e to the power n plus 1 divided by n over e to the power n. And you know, this is equal to n plus 1 e to the power n plus 1 times e to the power n. Okay, using laws of indices, we know if we add the powers, that means we're multiplying e to the power n times e to the power 1. So this is same as saying n plus 1 over e to the power n times e to the power 1 times e to the power n over n. And as you can see, we're going to cancel e into e to the power n into e to the power n. We're going to get 1. And after that, we're going to say 1 over e, this is a constant. Okay, n plus 1 over n. Okay, so this is the limit as n approaches infinite. Okay, so if we plug infinite here, we're going to get infinite over infinite, and we don't want that. Okay, so what we're going to say, we're going to say this is equal to 1 over e, and I'm going to divide each and every term by n. So this is going to be n over n plus 1 over n. Okay, so this is equal to 1 over e times 1 plus 1 over n. Okay, now what happens if I plug in infinite? I'm going to get 1 over e, 1 plus 1 over infinite. Okay, and 1 over infinite, you know that this is 0. So that means r is going to be 1 over e times 1 plus 0. That means r is going to be 1 over e. But you know that 1 over e, it's something like 1 divided by 2.7 is less than 0. So that means r is less than 0, and this series, it converges. Okay, now moving to the next question. This question, if you try to use all other tests except limit comparison test, I don't think we'll succeed, or it will take long. Okay, so what we want to do, we want to use the limit comparison test, and we want to have 1 on the numerator. Okay, and I don't think that is going to be a problem. So we're going to compute the limit of an, which is this series, over bn, which is a harmonic series. I don't think which series we're going to use, which you know its status, either does it converge or does it diverge. Okay, if we get L to be 0, let's say if we have L, which is the limit, to be 0, that means both series converges or both series diverges. So now our decision will not depend on our harmonic series. Okay, and if we get a number that is more than 0 and less than infinite, okay, that means both the series converges or diverges. And our decision, we get our decision from the harmonic series. I'm sorry for writing the shortcut, otherwise I'll run out of space. Okay, what if we get L to be infinite? That means if Bn diverges, An also diverges. Okay, and we'll get the decision, our decision from what? From our harmonic series. Okay, so first of all, let's try to have one on the numerator. So what we're going to do is we're going to multiply by the conjugate of n plus 1, root of n plus 1 minus root n. Okay, and if we do that, we're going to get n plus 1 root n. Do that on the numerator. So this is just changing the appearance. The value of the equation is just the same. Okay, you can multiply by a number. Okay, but you can't square. If you say this to the power 2 and this to the power 2, that is not equal. But if you say this multiplied by 2 and this multiplied by 2, it's equal or division, but not for squaring. Okay, so let's put some brackets. Put some brackets here. Okay, so that means our series now we have root n plus 1 times root n plus 1 minus root n plus 1. I'm just expanding. Okay, I should have multiplied by positive here so that I can have 1 on the numerator by plus 1. Okay, and if you do that, we're going to see here this is going to be root n plus 1 times root n plus 1. Okay, then root n plus 1 times n plus 1. So this should be positive. And now we're going to root n negative root n times root n plus 1. Okay, and minus root n times root n. Okay, and this whole thing divided by root n plus 1 plus root n. Okay, so if we, let's say, we know that root a times root a is equals to a. Okay, by the way, this is same as a to the power half. So if you have the same base, you can just add and you're going to get a to the power 1. So I'm going to do the same. That means we have a series. I'm just arranging my series in an order, in a simple order. Okay, so this is equal to n plus 1. Okay, here and here, these things will cancel. Okay, this will cancel, and we're going to be left with negative n over root n plus 1, or under the square root, plus root n. Okay, and we have succeeded. N minus 1, n minus n, it's now 0. So I'm left with root. Okay, let me expand here. Okay, so if we're given, let's say we're given, okay, root a times root b, that is same as saying root ab. So what I'm going to do is I'm going to say n plus 1, or under the square root, plus root n times n. Okay, and what is this equal to? So this is equal to n minus 4, n 1 here on the numerator. Okay, and here I have n squared plus n, or under the square root, plus n times n is n squared. The square root of n squared is n. Okay, and now it's time for me to complete the test, and I said I'm going to use the limit comparison test. Okay, so we have n squared inside the brackets. Okay, so that means we have n outside the bracket, but not the square root of n squared. If we factor out n squared here, we're going to get n. Okay, and we also have n here. So that means the best harmonic series, or the easy harmonic series, which I'm going to use is 1 over n. So I'm going to say limit as n approaches infinity of this series 1 over root n squared plus n divided by 1 over n. Okay, so this is same as saying I'm going to change it to the multiplication sign. The numerator becomes the denominator, so the same as saying n over n squared plus n. Okay, now I want to factor out n, so let's factorize here. Okay, if I factor out n squared here, I'm going to get n squared 1 plus 1 over n, or under the square root plus this n is independent of the square root. Okay, so I'm going to have something that looks like this. Okay, and we have said if we have n squared, you can just pull it out because you know the square root of n squared. So I'm going to say limit as n approaches infinity of n over n sort of 1 plus 1 over n plus n. Okay, this is same as saying n over n. Now I'm going to factor out n. From this, I'm going to be left with 1 plus 1 over n, still with the square root, plus, what about here, 1. Okay, and I think if we say n into n, we're going to get 1. And now we are left with 1 over the square root of 1 plus 1 over n plus 1. Okay, what happens if we plug in infinity? We said infinity of a number is 0, so this is same as saying 1 over the square root of 1 plus 0. Okay, plus 1. Okay, and what is the answer here? 1 plus root 1, that is equal to 1. 1 plus 1. So this is equal to 1/2. 1/2 is a number. Okay, so 1/2 is between 0 and infinity. Okay, so what is our conclusion? That means the series diverges or converges together, but we know that 1 over n diverges. So that means this series diverges. We're going to the next question. Okay, so in this problem, we're not given which test we're going to use. Okay, what if we think of the nth limit test? Okay, if we think of the nth limit test, we don't want 0. Okay, because if you get 0, that means the test will become inconclusive. But I don't think we'll succeed. Neither if we use ratio test. Okay, so what about we think of limit comparison test? Okay, so if we look at this question, again, I can use limit comparison test. Okay, I can think of my harmonic series. So in this case, I have n on the outside. What if I think of n squared? Okay, I'll think of n squared. So what I'm going to do is I'm going to find the limit. Okay, so I'm going to find the limit as n approaches infinite of this series, okay, of this series divided 1 over n squared minus 1, okay, divided by a series that I know it either converges or diverges, which I'm calling harmonic series, okay, but I have n squared inside the square root, so that means automatically I have n outside the square root, and I have this n, so that means I have n inside the square root and n outside the square root, so I have n squared. So I'm going to compare it with 1 divided by 1 over n squared, okay, and 1 over n squared, we know that this series converges because it's a p series of power 2, okay, so that means I am going to get a number which is not 0, okay, and if I get that number, that means this series, if this series converges, that means this series also converges, okay. So now let us compute the test. So this is, I'm going to call this, let me call this Vn, okay, and this is Un. So my test, I'm going to say limit as n approaches infinite of 1 over n squared minus 1 times n squared over 1, okay, this is equal to n squared n squared minus 1, okay, I can say n into n squared and I get n, so that means I now have n over n squared minus 1, okay. If I plug in infinite, I'll have infinite over infinite, and I don't want that. So let's try to pull this n out of the square root. So I'm going to factor out n. So let me say limit as n approaches infinite of n, and I'm going to factorize here. I'm going to factor out n. Okay, if I factor out n, I'm going to have 1 minus 1 over n squared, okay, and this whole thing is under the square root, okay. So if we have, let's say we have 8 root 8, okay, and we know that root 8 is equals to 4 times 2, the square root of 4, not the square root of 4, so that's why I get 2 root 2. We're going to apply the same concept here. We still have n on the numerator, the square root of n squared, you know that it's n, and now we have 1 minus 1 over n squared. So we have succeeded to eliminate n on the numerator, okay. So we're going to say the limit is n approaches infinite of 1 over 1 minus 1 over n squared, okay. So I'm going to say 1 over 1 minus 1 over infinite, and you know that any number of infinite that is 0, so we have 1 over root 1, and we have 1, okay. What happens if we have 1? 1 is not 0, okay. So we know that since our harmonic series 1 over n converges, so that means this series also converges. Going to the next question. Given a series and want to prove whether does it diverge or converge. Okay, so given we have a combination of powers and factorials, okay, I don't think the nth root, I think it will be difficult to use the nth root. What I'm going to use, I'm going to use the ratio test. Okay, so on the ratio test, you should just remember this. If we evaluate our limit and get a number that is greater than 1, and our limit in this case, we're saying our limit is r. If r is greater than 1, that means the series diverges, and if r is less than 1, the series converges. And you should know this result. The ratio test, we're going to say, okay, let me write it here. Limit as n approaches infinite, un plus 1. So that means I'm going to add 1 on wherever there's n. So I'm going to say 2, we have n here, so I'm going to say plus 1 times n factorial, but it's n, I'm going to say n plus 1 factorial divided by n plus 1 to the power n plus 1, and I'm going to divide that by our original series, 2 to the power n factorial, n to the power n. Okay, and you should be familiar with the laws of indices. Okay, so here this is same as saying 2 n plus 1 factorial, n plus 1 to the power n plus 1 times n factorial. Okay, so this is going to be, so it's n to the power n divided by 2 to the power n times n factorial. Okay, and now 2 to the power n plus 1, using the laws of indices, so we're going to say limit as n approaches infinite. This is same as saying 2 to the power n times 2, and we have n factorial here, so we have to cancel n factorial. Don't need n factorial, but you should remember that n plus 1 factorial is same as saying n plus 1 times n factorial, okay, over n plus 1 to the power n times n plus 1 to the power 1 times n to the power n over 2 to the power n times n factorial. Okay, so on factorials, I'm going to choose example of 9. Okay, 9 is 8. It's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so I want you to look 9. Okay, this is same as saying 9 times 8 factorial, because this is 8 factorial, and this is same as saying 9 times 8 times 7 factorial. And just look, what we're subtracting negative 1, we're saying 9 times 9 minus 1, okay, times 9 minus 2 factorial. So this is same as saying 8, 7. Okay, so that is the same we have done here. This is same. Instead of writing n plus 1 factorial, we said n plus 1 times n plus 1 minus 1 factorial. Okay, so this and this, this and this, this and this. Okay, and now we're left with limit as n approaches infinite of 2 to the power n over n plus 1 to the power n. 2 is a constant. Let's pull out the constant. Using the laws of indices, this is to the power n, this is n to the power n, and this is n plus 1 to the power n. We have the same power, so it's the same as saying n plus 1 or to the power n. Okay, and look, if we plug in infinity here, we're going to get infinity on top and infinity on the denominator, and we don't want that. So this is where this form comes in handy. 1 plus 1 over n to the power n. Okay, but unfortunately we have n plus 1 on the denominator, so we want to force things, so I want to change the appearance. We're not going to change the value of the equation. Okay, so I'm going to say limit as n approaches infinite to, okay, I want to write this form, I want to write this in form of this. I'm going to say 1 plus n over n, okay, to the power n. Okay, but if I just do that, look, I violated some mathematical principles, so I want to return back to this. So I'm going to say this is going to be to the power negative 1. So as you can see, this is same as this. And now I'm going to say 2. I'm going to divide each and every term by n. So I'm going to have 1 plus n, 1 divided by n plus 1 to the power n, or to the power negative 1. Okay, and the same as saying 2. Instead of writing this, we know this is equal to exponential to the power negative 1. So this is the same as 2 over e. And we know that r is less than 1. So that means this series, it converges. It converges. Okay. Going to the next question. Okay, so this is our question, and I'm not given which test I'm going to use. I'm not told. Okay. So what if we use the ratio test? Okay, if we use the ratio test, it is going to take a long time. And if we use the nth limit test, okay, we'll get 0. Okay, let's try the limit comparison test. Okay, so like I have stated, the limit comparison test are just going to say the limit of this series divided by the limit of the harmonic series you are going to use, which you know the status of it, either it converges or diverges. Okay, but we have a problem. We need a fraction that is 1 as its numerator. So in this case, if we say this function is, this series is over 1, okay, this series is not function. If we say this series is over 1, our numerator is not equal to, our numerator is not equal to 1. Okay, so what are we going to do? We have to, okay, let's try to rationalize the numerator. Okay, so if we multiply both the numerator and the denominator by n squared plus 1 plus, so that we can get 1 on top, n squared minus 1 over n squared plus 1 plus n squared minus 1. Okay, so this is same as saying we have multiplied this by 1, this by 1. As you can see, this can simply cancel. Okay, so what are we going to get? We're going to get okay, so if we are given, let's say we're going to use the laws of indices, we're going to do the same here. So we're going to get, we have n squared plus 1 times n squared plus 1. So we're going to get n squared plus 1, n squared plus 1 times n squared minus 1 plus n squared plus 1 times n squared minus 1. Then we have negative n squared minus 1 times negative times its positive n squared plus 1. Okay, and we have the negative n squared minus 1 times negative n squared minus 1. That means we're going to get n squared minus 1 and this whole thing we're going to divide it this with 1, so we're going to get n squared plus 1 plus n squared minus 1. Okay, means our series is now, you can see if we add this one and this one, you get 0. So I left with n squared plus 1 minus n squared plus 1 over n squared plus 1 plus n squared minus 1, and this is equal to 1 divided by n squared plus 1 plus n squared minus 1. So we know this is same as this, just change the appearance, but the value is still the same. And now we have to think of our harmonic series. So we have n squared here and we have n squared here. So what is going to be our harmonic series? Okay, so I am going to choose my harmonic series, which I know is status. Okay, so I'm going to choose, since I have n squared inside the square root, that means I have n. So I'm going to choose this series. I'm going to choose 1 over n. And I know this series converges. Okay. So we're going to use our formula. Limit as n approaches infinite of un over vn should give us the limit. Okay. So this is my vn and this is un. Okay, let's do that. That means we're going to get limit as n approaches infinite of 1 over n squared plus 1 plus n squared minus 1 divided, so I'm going to multiply, then I know the numerator becomes the denominator, n over 1. Okay, so limit as n approaches infinite of n squared plus 1 plus n squared minus 1. Okay, it's time to factorize. I'm going to factor out n squared, so I'm going to get n squared 1 plus 1 over n squared, but still inside the square root. Do the same here, n squared 1 minus 1 over n squared okay. So what I'm going to do, I'm going to say n, and I'm going to factor out n here, n root 1 plus 1 over n squared plus n root 1 minus 1 over n squared. Okay, and if we factorize, we're going to get n 1 plus 1 over n squared, and still under the square root, plus 1 minus 1 over n squared, still under the square root. As you can see, n and n are going to cancel out. We're going to be left with 1 over 1 plus 1 minus n squared, or under the square root, plus 1 minus 1 over n squared, or under the square root. Okay, and if we plug in infinite, then just write the limit as n approaches infinite. We said n number divided by infinite is equal to 0. So that means I will have the limit as n approaches infinite is going to be 1 over 1 plus 1 over infinite, that is going to be 0, plus 1 over infinite, so it's going to be 0, root 1. And you know this is same as 1 plus 1. It's going to be half. Okay. And since we have a number, we're going to, where are we going to get our decision? From our harmonic series 1 over n. 1 over n diverges. So that means this series also diverges. So it diverges. Okay. Going to the next question. Okay, so here I want to determine whether the series diverges or converges. Okay, so we're given 2 to the power n and n to the power number. So we're going to use the nth root test. Okay, so the nth root test is just saying we're going to take the nth root of this series and we're going to evaluate the limit, and the limit is equal to p. If p is greater than 1, then the series diverges, and if p is lesser than 1, the series converges. And if p should not be equal to 1, because if p is 1, that means it is becoming inconclusive. We have to use another test. Okay, so I'm going to do that here. Limit is n approaches infinite of nth root of 2 to the power n over n to the power 2013. Okay, so this is equal to, by using laws of indices, we know that root a equals to a to the power half, root nth root of a is equal to a to the power 1 over n. So that means here we're going to say 2 to the power n times 1 over n over n to the power 2013 times 1 over n. And to know by the laws of indices, if we have a to the power b, then a to the power b, let's say to the power c, this same as saying a to the power b times c. So that is what we have done here. So I'm going to say limit as n approaches infinite, limit as n approaches infinite of 2, because as you can see, n and n will cancel here. Okay, so this is same on the denominator. This is same as saying n to the power 1 over n to the power 2013. Okay, like this. Let's say if you are, let's say given a to the power 3. Okay, let's say a to the power b, and you have c. This same as saying the square root of a to the power b. So I'm going to say n, limit is n approaches infinite of 2. So this is still the same as nth root of n to the power 2013. Okay, and we know what is the nth root of n. We know that is equal to 1. So it's same like saying 1 to the power 2013, and 1 to the power a number is equal to 1. Okay, any positive number is equal to 1, so this is equal to 1. So 2 divided by 1 is equal to 2. Then our limit, which is p, is 2. Then we know that 2 is greater than 1. Then what is the conclusion? So the series diverges. Okay, thanks for watching. I hope for support in form of likes, comments, and subscribing.